this was the last slide that we were looking at. Now, you know, the thing that I was getting at here is a sample is taken from a population, as we said. It's important that that sample is representative, and we're making some kind of extrapolation from a sample statistic in the direction, excuse me, of a population parameter. We're not always doing that, okay? You know, I'm pointing out the semantics here, right, where the measurement on a population we refer to as a parameter, the measurement on a sample we consider as a statistic, but there's a deeper concept here, and that's that, you know, sampling is something that can be a repeated operation that we perform on a population. So if you think about that, you know, we've got, I don't know, let's say viewership data for Netflix or something like that. You know, what if we have such a mass amount of data that we can only at any given time look at, you know, 1/20th of some tabular data from that. Now, what we might do is sample that, you know, 1/20th at a time and start building statistics from that, and then resample, right? Resample from Netflix over and over again to build an idea of something like, what do we consider to be the mean of the mean number of hours people watch Netflix a day, right? Something as simple as that. But note that we can repeatedly sample, and we're going to a lot of the things that we write are going to look like that. I'm going to write some code to try to illustrate this a little bit. You know, this idea that we can repeatedly sample in order to approach something like a population parameter. Okay. So, what might this look like? If we're thinking about sampling, there's some randomness in that, right? We have to think about this in some random way. There's a function that you're going to end up using quite a lot called choice, and that lives in the random library. So to import that, I can say from random import choice, and what choice does, I can just demonstrate this really quick. Choice will choose randomly from a list of stuff, right? So 1, 2, and cat. I'm going to get one of those items, right? So we get cat, then we get 1, and then we get 2, and then we get 2 and cat. And, you know, if I do this, we're going to see that this is random enough for our purposes. Now, to kind of show this idea of, you know, drawing from a population in order to produce a sample, and then analyzing that sample in order to, you know, try to move a statistic toward a population parameter, what I'm going to do is, well, the first thing, we can consider a range of numbers, okay? I'm going to say that we have some sample range, and I'm just going to use the range function as it is, range from 0 to 99, inclusive of 99, so 99 plus 1. And even though I don't really need to do this, I'm going to cast it as a list. I don't know if y'all have seen this idea. Turns out that range, well, maybe I'll just demonstrate this really fast. Range, if I print a range from 0 to 99, oops. Notice this is what I get. This thing that says range 0 to, you know, 100. That's not very helpful if I'm trying to look at the actual numbers. So for our purposes right here, I'm casting this sample range to a list so that you know, if we want to just take a look at it, if I print this sample range, it gives us an actual list. A range is a type. You know, like a list is a type. A range is a type. We generally use range within for loops, that's where we see it the most, but we can use it easily outside of for loops as I'm doing here. Okay, so I am going to sample from this range, right? So I'm going to build a list called samples, and I'm going to sample 5 times. So for whatever in range 5, I'm going to append these samples, these 5 values that are sampled from the range 0 to 99 into this samples list. So I'm going to take a choice from the sample range. And if I print the mean of the sample range, well, we know what if we're considering this to be a population that is fairly uniformly distributed, let's say if we're going to expect that there's as many values of 90 as there are values of 1 and 97 and 23. We're not expecting there to be more of any one of those in this population of data, okay? And maybe we can even keep it so simple as to say, well, there's actually just 0 through 99, and each of those items is their own thing. And, there's only one of each. So there should be equal probability from grabbing any one of those. And if I print the mean of the sample range, let's see what happens. 49.5, wow, that's not bad, right? Oh, that's because I'm printing the mean of the sample range. Sorry, let me print the mean of the samples. That's actually what I meant to do. And yeah, because 49.5 is pretty good for like one draw. Anyway, we can look at these discrepancies. The discrepancy between what we expect, right? Here's our population mean. I'll just call it that. I'll say I'll just call it mu. And okay. And then call this x bar. Okay. So 49.5 and 65.5, right? 49.5, 68.8. And it's not that x bar, from some random draw, it's not that it won't get close to the mean, the population mean sometimes, right? X bar will get close to mu sometimes. Now, what happens if we build x bar over and over again, right? What happens if we build x bar over and over again, sample x bar, and then take the mean of the means, right? We take the mean of the means, we are going to be getting close to 49.5 pretty quickly, actually, pretty quickly. I'm not going to do that here. Think about how to do that, though. It's not hard. It's a little bit of loopage and, throwing stuff into a list, and you get there pretty quick. And you can even, here's the cool thing, you can even just try to figure out how many samples it's going to take to get within a certain bounds of the population parameter, right? And that starts getting us into the family of things associated with confidence. Like what size sample? How many samples do we need to take for some type of data to be approaching a population, or to, hopefully, theoretically, be approaching a population parameter. Not everything is about approaching a population parameter. I do want to be clear about that. There's actually something we're going to talk about today that most people assume is about approaching a population parameter, and it's not. But doesn't have great import. It's just the type of misconception that happens in statistics a lot, and I'll probably talk about that a little bit when we get to it, because I think it's really interesting. And also not of great consequence for where we're all at. So I'll try not to spend too much time on it. Okay, So now we're getting into the second part of our summary stats, okay? We've considered these ideas of central tendency, when we're thinking about what is representative of the data. What do we expect to see when we look at the data? And now we want to qualify what we expect to see through an idea of variance, of spread of the data, right? Because maybe we do expect to see the mean. But, if you think about a distribution of data, well, before I use that word too freely, oh, wow, that's cool. Okay, sorry. Okay, so if we're thinking about some data, and we have, let's have some range of values from 0, well, let's just do 0 to 100, right? And the way that I was talking about our data just now, every value in here had equal probability, right? Equal likelihood of being drawn in this random approach. So, we have essentially what we might consider a flat distribution, a uniform distribution. When we talk about distributions, we'll talk about that more specifically. But what if we had a whole bunch more of the value, say 25, in another distribution, right? So somewhere around here in some other distribution, we have a whole bunch of 25. And then we have almost no, let's say we have one value of 50. And then we have, a fair number of the value 60 and a whole bunch of the values right in the 90 range. And let's say that there's some smoothness here, and this distribution looks like something like this. Okay, so and let's still consider it to be discrete. Let's not say there's a 1.5 or a 3.7 or anything like that. These are all discrete, so this smooth line should actually be flat, but that's okay. We can deal with this as it is, but just don't be misled by the smoothness of it. It's just easier to draw smoothness than a whole bunch of 100 stair steps, which I'd rather not do right now. So notice that we have a lot of this value 25, and we have only say one of this value 50, and then 60 we have more of, and then 90 we have more of, but not quite as much as 25. If we work this out, and the reason I sort of built it this way, there's a chance that our mu here is in fact 50, right? There, when I'm looking at this, my intuition is saying, okay, well, it may be kind of like imbalanced in some ways. Like it's what we might call multimodal, right? This might be a multimodal distribution. And by multimodal, I just mean, well, we've got a first mode here, and we've got a second mode here, and a third mode here. We might call this multimodal, but we might still have a mu, a population mean at 50. Okay, so that's something that we need to recognize. If we think about this, though, what is a representative value in this case? Because this the population mean is not going to tell us what we it's like, well, on average that's what we should get, but we're much more likely to get the value 25 than we are to get the value 50, right? So this leads us to an idea of, well, we can't just talk about the centrality of the data. We have to talk about how the data is spread. And the ways that we're going to do that, there are 4 ways that we're going to think about this. And when I say 4, I really mean 3. But we're going to think about this through a classical idea called the five-number summary, IQR, which we can get from the five-number summary, and then variance. And standard deviation is a transformation of variance. So we can think about these as really being the same thing. In general, when you report on centrality of some data, you're going to say, okay, well, there's a mean of this and a standard deviation of this. That's common parlance. If you've read scientific journals, studies, medical studies, anything like that, there's always reporting of mean alongside standard deviation or variance, and that's in part for this reason, right? Where we need to think about the shape of the distribution, not just the centrality of it. So, with that in mind, let's talk about some measures of spread. We'll start off with five-number summary. This is fairly simple, and it's easy to explain. And I think that's part of why it has persistence in the statistics space. It's immediately helpful to get a clear idea of what's going on in some data. And the more you work with five-number summaries, the more intuitive they become. So here are the questions we might ask. Well, what is the smallest numeric value? What's the largest numeric value? So we have minimum and maximum. And then we have the median, right? What is that middle spot in the data? And then what is the middle between the minimum and the median, which we call Q1? And what is the middle between the median and the maximum, which we call Q3? So I think when you look at this, it's possible to see, if you have this data that maybe it's sparse, for some range of numbers, well, that's going to spread out the, your minimum and median from your Q1, right? There's going to be more gap there, and we can see that. We can sort of visualize that fairly easily with box plots, which we don't really cover plotting in this course, but the materials on Learn go into some depth on those. We tend to use box plots and violin plots quite a bit, and those are, representative of five-number summaries. So this concept hasn't gone away by any means, but it is a little bit more in the classic statistics space, and people do have a little bit of a harder time reading them unless they're more familiar with them. So you might see them a little less often than you might see some other kinds of plots. So I'm going to have you code the five-number summary, okay? And you know what? Let me leave that slide up, actually, because these are all things that we know how to do, okay? You know how to get the minimum and the maximum, right? That's just the min function and the max function. And you know how to get the median. So the median, we've got a function for that, right? We have that. And you should definitely use your existing median function, right? So that's in summarystats.py. If you need it, I'll paste it in. I guess you'll need the mean function as well, just in case. Oh my gosh. Okay. So let me paste those in. If you're not working in the same document, you'll need this. So there's median and mean. Median is dependent on mean in my implementation. So I just put these in the wrong order. So you'll probably want to just put mean above median, but either way. And let's see. Yeah, and I'm going to give you 5 minutes on this. And if you have questions about it, post them in the Slack. I'll do my best to answer those questions there, or if there's something that's really outstanding, I will come off mute and start answering. But yeah, for the breakout, the name that you're going to define is just 5-number summary. So I'll put this up there as well. Okay, I'm going to set a timer. Got 5 minutes, and this function I will probably if down at the 1 minute mark I ask if you need more time and you give me thumbs up, I'm going to give you like 2-3 more minutes. So yeah, keep that in mind. All right, go to it. Okay, this is the point where I ask you, do you need a couple more minutes on this? And if you do, give me a thumbs up. And that's totally cool if you do. Okay, cool. I'm going to put 3 more minutes on this. And yeah, just try to get there. If you don't get there, it's also totally okay. We'll walk through this pretty in depth. Okay, so I'm going to start working through this. And I'm going to try to do this in a very accessible way. And I might, modify the code a little bit to be slightly more Pythonic, but not, not excessively so. So we're going to call this 5-number summary. And we're going to pass in a list, right? So at this point, I'm not always going to do this, but in general, I think it's helpful for you to create your data first, right? And so I'm going to do that. I'm going to call this, test data, and I'm just going to do the range from 0 to, about from 1 to 100. And that's what I'm going to call when I that's the thing I'm going to pass into the function when I call it. So test data. Okay. So now that I've got that, I can easily I can easily go down here and do Python summary. Oh, probably need to save my file first. I can run that, and immediately I see an error. Actually, that's a good thing to see. Line 103, test at list range 1 to 100 plus 1. Oh, well, that makes sense. You can't have a function that doesn't have something in it. Okay, cool. So we know that the test is set up. And then I can start coding this. Well, what do we need? We need the min. So I'm going to get that first. That's easy enough. I'll just get the min from list. This is a habit I have whereas I would call this min in general, but min is also a reserved word, right? So I'm going to do min underscore instead of min. And then we need the max. We know we're going to need that. So I'll get the max. Again, that's easy. So I've already got 2 of the 5 things we need. And then I need the median, right? So we have a median function, and that median function is going to effectively process the median from a list. So already we've got 3 of the things we need. And the order that this is going to go in, right, we're going to return the min, then Q1, which doesn't exist yet, and then the median, then Q3, which doesn't exist yet, and then the max. So at this stage, I could just run this again, make sure I'm getting something 1, 50.5, and 100. That's reasonable, right? That's from 1 to 100. Our median should be 50.5 because it's between 50 and 51. So let's go from here. So the thing that may not be immediately obvious is that we need to create an upper and lower portion of our list. And maybe, since this returned 50.5, 50.5 is not a member of our data because we have an even length list of data. So I'm going to call this even test data. And then I'm going to do, I'm also going to do odd test data. And this one I'll go from 0 to 100. And that way we're testing both cases, right? So even, odd, and let's see where that gets us. So that makes sense. 1 to 100, 50.5 as the median, 0 to 100, 50 as the median. So that is working how we'd expect it to work. All right. We need Q3 and Q1, right? So those are just the medians of the upper and lower halves. So we need to create slices of our original list that contain the upper and lower halves. Notice that is contingent on the list being sorted. So why don't we do that? So sorted list is going to get the sorted version of the list. That's easy. Now we're working with a sorted version. And I'm going to do this. I'm going to do this in a longer way, but there are ways to do this with more compact code. So the first thing, I'm going to check whether or not the list is even or odd. So if the length of the list modulo 2 is 1, then we know it's odd. What's another way? Anybody have a thought on another way that I could, given what I have above, given this value of median, how could I check to see if this is an even or odd length list? What would be a way to do that? Any thoughts on that? Well, if something occurs to you that would also be the same condition. Okay, yeah, exactly. There are 2 different ways that are different, right? They are really different. So we've got 3 different ways to check this. One way is if the length we can do this modulo operation. We can also check for membership of the median in the list, right? If median in list, well, then we know it's even, right? If median not in list, we know it's odd because we have some decimal value. We could also check if it's a float. So any of those would work. So we have this condition, and I'm just going to do this. I'm going to set, say, well, we have this lower half, and the lower half is going to be the sorted version of the list. And we're going to start it at the 0th item, and we're going to go up to the length of the list divided by 2. Now, anytime we do division, of course, it's a float. So this would be, we need to actually cast that to an integer, like so. So that should work for our lower half. And then the upper half is going to be something very similar to this. We can say the sorted list, except now we didn't include this value in the lower half. We are going to include it in the upper half. And we can, the way that we're going to do that is we're going to add 1. Now, why is that? Why are we adding 1? Now, this is an argument that people can have about the 5-number summary, or how we think of Q1 and Q3. Do we include the median in the calculation for Q1? In general, most people will not. I actually learned from my stats class, one of my stats professors, to actually include the median in the calculation. Here, but the common practice is to exclude it. It does make a big difference in certain instances. In this instance, it won't be that different. So if we're looking at that odd length list, we're not going to include 50 in the calculation. We're going to get the median between 0 and 49, and then between 51 and 100. Okay, and that's where this +1 is coming from, right here. Okay, so that's if we have an odd length list, and if we have an even length list, this is going to be a little different, but not much. So in this case, this lower half is the same, and the upper half, we just get rid of the +1, right? Because as we're seeing here, 50.5 as the median is not actually in the list. So we can include 50, we can include 51. 50 will be included in the lower half, 51 will be included in the upper half. So this is kind of, you might be looking at this and you might be thinking, well, there's some redundancy there. Can you think of a way to eliminate this redundancy, where we basically have lines 107 and 108 mirrored at 110 and 111? We can actually condense this down, and I'll show you how to do that in a second. So let me just add in our calculations for Q1. Right? Q1 is just the median of the lower half, and Q3 is the median of the upper half. And that should be, unless there's some error in here, that should be a working function. So let's find out. It's not, because I am not doing anything here. So modulo 2. Okay. And now we can look at these outright. And what we're seeing between 0 and 50, we're seeing 24.5. Now, why is that 24.5 and not 25? It's because 0 is in there, right? Like, if you think about the range of numbers from 0 to 100, that's 101 numbers. And that's why we're seeing this pulled to one side or the other, because there's the inclusion of one number or the other. And in this case, since we're starting at 1 and going to 100, we're getting 25.5 as Q1 and 75.5 as 100. And maybe this will be a little nicer to look at if I change this from 0 to 99 plus 1 instead. Oh, actually, No, I'm gonna have to think about that a little bit. I might have something a little off in here. But let's refactor this just slightly and get rid of this redundancy. Notice that length of list modulo 2, if this is 1. Well, if this is 1, we can actually take this out of here. And we can do this. We can replace that plus 1 like so, and get rid of all that, okay? So I've removed the conditional statement and I've thrown this plus 1 in as sort of like a addition on condition, if that makes sense. Okay. And we get the same result when we look at it like that. All right, so we could take this further, right? I could actually eliminate this code, and you know, I could condense all of this down to a really not very friendly line. And I just want to point this out. I'm not saying you should do this. I could take this. This is our Q1, and I could do something like median of all of that, and then take the median of all of this for Q3, right? And suddenly we have a much shorter function. And I could make this even more terrible to read, that is. This is actually completely legitimate code. It's just sort of awful to read. And I could, oops. I'm going to see how dense I can actually make this. And the only thing, let's see, I can replace median in the return statement with that. And then the only other thing I would need to do here if I wanted to make this actually condensed is replace this sorted list here and here. And now we have a one-line function. Let's see if that still works. It does. This is the same exact logic, okay? But I've just condensed it down into one terrible to read thing. I am not recommending you do this, okay? Just to be very clear, I'm not recommending you do this. For your sake, sure, but for other people's sake. If somebody comes across this, they're not going to be able to read it. And, you know, you can break this logic out, and that logic will be understandable. Now, you know, if you're writing this and everyone on your team is like, yeah, this is good, then you're good, right? Then don't worry about it. At that point, you're probably not going to be writing this function in quite this way, but I'm going to leave this here in summarystats.py. There's a longer form of this in the slides. So, you know, this is for your own, like, if you want to, like, read through it and, you know, try to break it out and think about it that way. In Python, we do write a lot of condensed stuff sometimes. It's sort of like a extreme coding sport sometimes, where people are like, hey, can I turn this really complex thing into one unreadable line? Yes, I definitely can. Okay, so let's do another quick break. Oh, you know what? Let me give you that terrible function I just wrote, in case you don't have a working 5-number summary function. And this should work. And let's do a breakout where we apply it, okay? So let me grab that. Okay. So this will be pretty quick. Let's do 3 minutes on this. Calculate the 5-number summary. What is the mean? And what do you consider to be the best measure of centrality for the data? So I'll put 3 minutes on the timer. And yeah, let's see what you think about that. Yes, sorry about that. That would I'll paste in the data. That'll make it way easier to get to that. And I'll also restart the timer. Sorry about that. Wasn't thinking. Let's see. Okay, so I'm going to start working through solving this. And just put this up here. Now, sorry, every time I do that, I'm actually switching between windows to look at Slack and stuff like that. It's not just my computer being chaotic. Okay, so let me paste in the data. That's A and B. Okay. So the first thing that we're going to think about is the 5-number summary. For this, I tend to like to actually look at the data in a sorted way. So I'm going to do that. I'll put that in first. So we'll print the sorted version of the data. And then I'll print the 5-number summary of A. And then I'll print the mean of A. And even though we already have it, I'll just print the median of A as well. Okay, so let's look at that. So let me grab all of that. So looking at this, 1, 5, 9, 18, 27. 9 is the median here, so we're seeing that right there. So there's our median, and our mean is right about there. And Q1 is there, and Q3 is there. Okay, so what is a better measure of centrality in this? Honestly, I think 9 or 11 seems pretty reasonable. I would go with 11 on this over 9, and part of that is think about how these numbers are spread, right? So there's a difference of 3 here and a difference of 3 here. 1 and then 8. And then if we're looking over here, there's a difference of 1 and then 3 and then 1 and 2. So to me, 9 is a little less representative. Then that's just me, kind of thinking out loud as to why I think of 11 as being a little more representative here. So that's for A. Let's look at B. It's nice because we can just, how about I do this? Def output breakout. Let's do that. And we'll pass in a list, and then we'll just change this to list all the way through. Oh, that's not gonna work. Okay, and that might be a little bit more compact. So there's A, and then here's B, and maybe I'll just put an empty print down there as well. Okay. So when we're looking at B, this might, We'll consider the mean versus the median here. And just notice this is, fairly different data, right? So 19 is our median. So that's right in here. That's our median. And then I'm sorry, that is not our median. Not at all. Let me just cross that out. No. I am sorry. That is our median. Sorry. I probably should have labeled these down here so that I don't confuse myself. And then when we look at our mean, it's all the way out here, right? So, really, I should call that X bar just to be consistent. So, if I'm looking at this, I don't know. I could make an argument for either of these. My intuition is saying median, and I honestly offhand I can't tell you exactly why. I'd have to think about this a little bit more. Let's think about the spacings between these, how the data is spread. I think since this data is spread in some way fairly consistently, Um, you know what? I would go with mu. I would go with x bar on this because that does look more like the centrality of the data to me. Even though it's sort of off to the right a little bit more than I'd like, it does seem more representative given that we have these higher values that are more spread and these lower values that are less spread. Now, we'd have to look at the data itself and figure out, well, why are the higher values more spread? That starts becoming important. Maybe it's an issue with our sampling, but, in this case, I think you could make an argument for either, although I'm leaning toward X bar. All right. Let's take a break here, and let's do 6 minutes. And when we come back, we'll just continue in the same vein. The place where we're going to round out today is in variance and standard deviation, and that's going to come up quite a bit in distribution. So I'm going to try to make sure we budget time for that, and we might even continue that into the next lecture if we run out of time today. Okay, so I'll see you back here in 6 minutes. Okay, there's a really good question in here that leads me to want to clarify something that I was saying that because I don't want to mislead you into thinking that it's a battle between mean versus median. It's really not. Both of these are descriptors on the data, and I put a short message in the Slack saying that. And yeah, there are a bunch of other metrics that we don't include here that I think are really helpful, and they're helpful for different reasons at different times. But at the end of the day, it's getting to know the data. This is something that when you're in this space. Oh, am I on mute?
We can hear you.
Okay, cool. Thanks. Sorry. Okay. Yeah. So when you get into this space, one of the things that you start doing is looking into like the minute details. You get to know data. You get to know data in a way that people won't understand. I think I alluded to this before, but let's say here's an example from my experience. I was talking with a friend about creating a generative podcast, where it's text to speech engines that are use their prior conversations to generate new conversations. And we were just talking about this, funny, dorky thing that we could do. And it would just get progressively, assuming it would get progressively worse, more jumbled, more terrible as time went on, and which was part of the goal. And we're just talking about this, and somebody approached me and handed me an iPad and was like, and there was like a lacrosse game on it, and he asked, could you automatically detect when a goal is scored, right? So this is I don't know anything about lacrosse, by the way. I've never played it. I don't really understand it. And then I spent the next couple months building networks on lacrosse footage to do player segmentation and to determine when and to tag the video for when a goal is scored, like automatically. Like there are these things that people do in lacrosse games, like they'll score a goal and then they sort of condense around each other in this very specific way that you can fairly easily detect. You don't even really need machine learning to do that. It's kind of like it's ritualistic, right? And it's this human ritual, and you can detect these things, right? And having never played lacrosse, never had any exposure to it, I still don't, I don't know how the game is played, but I know a lot about lacrosse in a way that other people don't know, right? And so you build a relationship with data that is absurd sometimes when you get down into it. Like you don't know what the domain experts know, but you know so much of what the domain experts don't know, right? Because you're going through this and you're getting to know it in a very different way. And so, just tying this back to this idea of mean and median, they're not really at odds, right? They're both descriptors. And, there are times where we're thinking about in terms of what we report to somebody as representative. And that's when I'm saying this, like mean versus median, kind of thing. Really what I'm saying is like, hey, you're talking to, somebody, you're talking to a CEO, you're talking, what are you representing as what are you representing as definitive of the data, of a description of the data? Is it, there are times where median is going to be very unhelpful and mean will be helpful, or vice versa. And when we're saying that, like, which is better, it's more about which is better for reporting. They're both just descriptors, though, at the end of the day. And the relationship is informative to us as we view it. Okay. So I just wanted to qualify that because I think I have been representing these as being at odds in some way. So here's a nice thing about the 5-number summary. We can get another measurement out of it called the interquartile range. And this is just, the set of data that's in the middle. So instead of having an upper and lower half, we can say, well, most of the data is in here. Most of the data, 50% of the data, sorry, I said most, 50% of the data is between Q3 and Q1. And this is a very simple function to write. It's just Q3 minus Q1, right? So let's do, this says 4 minutes. I'm going to just code this really quick because I think of this as being pretty straightforward. And I think there's a more interesting function that we're going to use out of this. So here we've got, two lists of data, A and B. And we're going to code the IQR function. Make that a little bit bigger. So this is going to be the IQR of a list. If you have a thought about how I might do this, given that the IQR is simply Q3 minus Q1, go ahead and put it in the Slack. I think when I code this, it'll be fairly obvious, that this is a simple function to write, given what we've already written. Let's see. Did I? Oh, good. Okay. I just wanted to make sure that I shared the 5-number summary function. All right. So for us, we can just simply call the 5-number summary function, right, and get Q3 and Q1 out of it. So this is going to be 5-number summary. I'll wait for that to suggest. And we're going to pass in that list. And remember, we get out of this the min, Q1, the median, Q3, and the max. But we only need Q1 and Q3, right? So what I'm going to do, this is a shorthand that I like a lot in Python. This underscore just means that we don't care about it, right? Like we don't need it. So this is kind of a disposable variable. I'll do this a lot when we sample, right? Because we don't care about what sample number we're taking at that moment usually. What we do care about is the result of sampling. So yeah, this just means that we don't care about it, but it is one of the things returned by the 5-number summary. And then all this is going to be is return Q3 minus Q1, and we can then get the IQR from both of these lists. So we've got this range from 0 to 50 by 5s and 0 to 100 by 5s. So let's take a look at what those IQRs are. IQR of A and B. So 30 and 55.5. Now, in context, well, we don't need to sort that, actually. In context, when we look at these lists of numbers, well, the interquartile range, if we think about where our median lies, the interquartile range is going to be this section right here in the middle, right? Or this section right here in the middle. So it's just the width of the middle of the data. IQR is, again, it's a descriptor, right? It's a descriptor of numeric data. We can say, okay, well, the middle 50% of the data is constrained to this, right? It's just a range of that. It's a width of that. And that gives us a sense of the scale of our data, right? But it also gives us a sort of clarity on what might be representative in the data. So let's think about this in terms of the concept of an outlier. Is IQR inclusive of Q3? Huh. I never thought about that. I think it is. I think it is inclusive of Q3. We can check pretty easily here. So why don't we print the median as well? So we'll print the median of A and the median of B. So the median is 25, and we go, 15 up from 25. We get 40, 15 down. Yeah, I think of it as being inclusive. I'm trying to think if I'm incorrect in that thinking. It's such a it's funny because it's such a basic thing, and I can't answer that question. I think I'm just tempted to Google it right now. I'll Google it afterward, and or maybe when we're in questions. But to me, it is inclusive, right? It seems like it should be. The way that we're going to think about IQR, though, is in terms of determining outliers. Okay, so it is a descriptor and everything. To be honest, in our realm, in the data science realm, I am very, in the things I do at least, I'm very rarely looking at 5-number summaries or IQR. It's more in the classic statistics spaces, or in specific domains, like in finance. I think you look at IQR a lot. In sports statistics, definitely you look at things like that, or you look at those metrics. But where the only place I actually really use IQR is in an automatic determining of outliers. So if we think about what might be an outlier, we take that that range of the middle 50%, and we multiply it by 1.5. Although we could set an arbitrarily different value, like 1 or 3 or something like that, depending on our data. Right? This is an arbitrary metric, just to be very clear, or an arbitrary procedure. So we take 1.5, we multiply it by the IQR, and if a value is greater than 1.5 times the IQR above Q3, then it's an outlier out to the right. If it's 1.5 times the IQR less than Q1, then it's an outlier off to the left. So that's a fairly simple concept that can, just help you to determine when you're looking at your data, should I keep this or should I not? Now, this doesn't apply to all data, right? Like in those housing prices, for instance, we might detect outliers, but those may not actually be outliers. They just may be indicative of the data itself. So something I want to point out here, because I'm going to have you write this function very shortly. 1.5 times the IQR, and maybe I'll just make this bigger again. So when we're thinking about this value, 1.5, I'm going to call this an outlier coefficient, okay? So outlier coefficient. We could make this 2. We could make it 3. We could make it 5. We could make it some other value. And when you write your detect outliers function, I'm going to put an optional second parameter in there. And your goal is to include that second parameter of outlier coefficient and use that when you write this. So I just want to point that out. It doesn't have to be 1.5. It's just 1.5 is sort of the standard. Okay. Well, that's creative. Okay. I'm going to paste in a little bit of starter code. And this is just the function definition with both of the parameters, both the list and the outlier coefficient. Okay, so yeah, you're going to write detect outliers. The easiest way to think about this is in terms of calling out to IQR. In fact, let me give you the IQR function because I don't think I pasted that in, and you will need it. right, I think you should have everything you need. And let's do 4 minutes on this. Yeah. Okay, go for it. Okay, I'm not seeing any solutions posted. Give me a thumbs up if you want another 2 minutes on this, if y'all are working on it. Okay, yeah, let's do another 2 minutes on this. Okay, I'm going to. This isn't the easiest function to write, and I'm gonna go ahead and start coding through it. If you feel like you're almost there, keep coding, and if you feel like you're not going to get there right now, go ahead and jump on. So I'm going to write detect outliers and pass in a list, and we've got this outlier coefficient. By default, that will be 1.5. Okay. Now, the first thing we're going to call is the 5-number summary, right? That's where we're going to get what we need. So let's get that, and we're going to need Q1, Q3. I don't think we need anything else. We just need Q1 and Q3. And then I'm also just going to, even though this may seem redundant in some way, I'm just going to call the IQR function on that list. So we have Q1, Q3, and the IQR. And that's what we need, right? Like when we look at the formula for this, or the reasoning for this, which I'll put back up here, any data point in the list that is 1.5 times the IQR above Q3 or 1.5 times the IQR below Q1, we're going to get rid of. So let's just think about that in terms of a for loop. So I can just say, well, in this function, we're going to return outliers in a list. And if we have no outliers, we return an empty list. That was how the prompt was written. So for each number in the list, if that number is less than Q1 minus the outlier coefficient times the IQR, which I named as that. If that's true, right, then we can just append that number to outliers. And the other condition that we might consider is if that number is greater than Q3 plus the outlier coefficient. And yeah, so that's fairly simple, right? That's fairly straightforward, and then we can just return the outliers. So let's think about, I'm going to think about this in terms of, I'm going to generate a list that has a clear outlier, okay? So let's test outliers on a list from range 0 to 100. If you think about this, there will be no outliers in here, right? And we can check that. We can say detect outliers on this test outliers list. And what we should see here when I print this, and yeah, let's just do that. I'll just print that. I don't need to print the list. What we should see here is an empty list, and that's what we're seeing. Now, what happens if we append to this a large value? So let's append to this 90,000. This is 0 to 100. 90,000 does seem like an outlier, right? There's I think it's fair to assume that 90,000 would be an outlier, and we are getting that from the list. Well, let's put another outlier in there. Let's put let's test the bounds of this. Let's put 5,000 in there. My intuition says 5,000 is an outlier, and it is, right? 1.5 times essentially 50 is not going to be as large as 5,000. So we can see that this is working. We're collecting, in this case, the outliers. So let me go ahead and paste this in. And there are other ways to get to the same solution. One thing I might do is just condense this into, you know, something like that. That's a little less code, but this statement is pretty long, right? You don't need to necessarily do that. I do think this is a little bit more descriptive. I think in some cases you're going to be tempted to do an if-else, but this is not an if-else, right? It's an if and then another if, because there is no data. This is where logical errors happen. There is data that doesn't qualify as an outlier. So we've got that. This kind of takes us to another idea. Well, what if we want to remove outliers from a list of data? And I'm going to, let's see. Let's do this. I'm going to skip the next breakout, and I'm going to go straight to this breakout, another breakout prompt, where I'm going to write, I'm actually going to walk us through this one, write a function called remove outliers, okay, that takes a list of data, and it returns a new list with all the values that are not outliers, okay? So I'm going to reuse this data here. I'll just give a little bit of real estate. And I'm going to write this remove outliers. So how do we want to think about this? Well, we've got a function that can detect outliers, right? So we can find those values and just remove them from our data set. Now, how should we do that? There's a few ways we might think about doing that. And I'm going to write this in one way, and I want to see if y'all have an idea of an edge case where this isn't going to work. So be thinking about, or where this might fail a little bit. Let's say it like that. I'm going to pass in a list, right? And an outlier coefficient, because that's what we need for our other function. So outlier coefficient, and we'll again default that to 1.5. So our outliers we can get from detect outliers of the list and passing in the outlier coefficient. Okay, so we've got our outliers now. What I could do, one thing I could do, is I could say, okay, for outlier, well, maybe I could do this. I could say, let's try this. For outlier in outliers, so I'm going to take each one of these outliers, and I'm going to say, if the outlier is not in our list, or sorry, is in our list, then list.remove the outlier. And maybe at the end of this, I return the list. Okay, so some of you might already see something a little bit not great about this approach. This is sort of an obvious approach that we could take. But there's also a logical problem in here. And I'm going to try to demonstrate that shortly. So here we've got detect outliers. We're assuming that, this has these two outliers, 90,000 and 5,000. And if I pass in our test outliers, so this first function call, we detect the outliers, and then we should see a list with the outliers removed. So let's see if that's what we get. And I'm not seeing 90,000 or 5,000 in there, in this big wall of whatever. Maybe I'll make that a little smaller, right? So let's do 0 to 20, just to be a little more compact. So that looks like it's been cleaned. Now, any thoughts as to a logical issue with this? This looks like it's working, but there's something a little bit wrong with it. Actually, there's a couple things a little bit wrong with it. And yeah, does anybody have a sense of what that might be? That's one of the things. Yes, the list is being mutated. Now, that's fine in some sense, right? That's not illegal, right? But we don't really want to do that. So we could, correct that by saying, I could, just quickly do something like that. And now we're not mutating the list. So that's one thing. The list is revised. Yeah, so everyone's seeing one of the issues, but that's more like a stylistic issue. It's not really a problem unless it is, right? In this case, it's not, but it's also something that we should all avoid doing if we can help it, or unless it's specifically something that we need to do, or we want to do, like in graphics programming we often do. What is the reason for the outlier? Well, that's more the philosophical side. Either way, these outliers are pretty extreme, right? I don't think that... I think we could make let's just make the argument that these outliers are definitely not supposed to be there. There's another issue. There's an actual procedural, logical issue with the way that I'm doing this. And it may not be entirely clear, which is fine, right? Yes, that's exactly right. It's not going to remove multiple instances of the outliers. And this is the reason I'm pointing this out. Oh, wait a minute. It is removing multiple instances of the outliers. Oh my gosh. Okay. Sorry, I was trying to write a broken algorithm, and I wrote an algorithm that still worked, and that was not my intention. Okay, let me just retract this. This does work, but so this is a reductive approach, and it's fine. And the only issue is the issue that y'all pointed out. The issue that I was looking for is not actually true, even though I meant for it to be true. So, well, there's that. In this case, because we are compiling this outlier list, 90,000 will appear in there multiple times, and it will be removed each time. In cases like this, it's interesting because this approach, this reductive approach, is better. It's less iterations of the loop than if we were to... and what I'll do really quick is rewrite this, and then I'll remove the part that I rewrite. And this is just a subtle optimization thing, but we still need these outliers, so I'll grab that. So we get our outliers, and then we're gonna, instead of reducing the list, what we're gonna do instead is have an additive approach. And I just want to point out that this is going to take more iterations of the for loop. When it's all said and done, it doesn't really make a difference computationally, because we throw away, the number of times the loop runs in some sense when we are considering performance, time performance. But if you want to write slightly better code, sometimes the reductive approach is better, right? Because we're reducing out this outliers list, which is should be smaller than the input list, right? So for each num in the list, if that number is not in the outliers, then we can append it to output, right? And then at the end of all this, we can just return output. So the way that I was thinking about this, misthinking this, was thinking of outliers as being the set of values that are outside of a given range, which is not the case, right? And we could logically construct this so that it wouldn't work in this reductive approach, but I accidentally made it work. So sorry for sorry for that. I'm like asking you a question that that doesn't exist. Okay. All right. So we have this approach for removing outliers that works, and we can change the coefficient, pretty dramatically, right? In this case, when we're thinking about it, we might even ask a question like, well, what if we have an outlier coefficient of 5, let's say? Are we still going to remove those outliers? We are, right? Because these outliers are very extreme. Like how many times do we have to actually, like we're still removing them, right? Because again, these outliers are really extreme. Okay. So from here, we're going to move on to, yes, I will share this function. All right, so this kind of gets us out of our sort of classic stats. And I want to say just a last thought about this outlier issue. In more cases than not, we're not going to be removing outliers. We're going to be talking about why those measurements are in our data. The bigger battle, and this is a battle in data collection. The bigger battle is missing data, actually, or corrupted data, or dirty data, right? When we have sensors that are reading things, when we have things that are reported. For example, let's see, last year around this time, I was teaching out of, there was a lecture I did using the EU, the Data Europa COVID-19 data set, which is, just the frequency, the COVID frequency across the world, reported by country. And there were things in that data that were broken, right? There were times where there was missing data. There were negative reported COVID cases, things like that. And when that happens, it's actually really helpful in a way, because you can say, well, what's happening here, right? We have negative 3,000 cases on this one day in some country. How do we interpret that? Is that a retraction of a reported number, or is it a clerical error happening on a global scale, right? And how do we find that out? So, anomalies in data. This is, if we start thinking about this less as removing outliers and more as detecting anomalies, then we can have a better relationship with why something is happening the way it's happening. Like, what caused this? And is this something happening in the operational collection of the data, or is it something happening because of sensor failure? However we want to think about that. The bane of our existence is not outliers. It's actually missing data. And the tendency in terms of missing data is that we either have to generate that data, impute data is what that looks like, or is how we talk about that, or we have to throw that data away. And what you'll find is that, you find some data and it's this huge data set and you're like, I'm going to do great stuff with this. And then you throw away a third of the data or 2/3 of the data because it's so corrupted. And you realize that you are missing a great deal of the things that you need to work with in order to do the thing that you thought you could do with what's sitting in front of you. An example, actually, I was working on this with Lance Bardo, whom some of you have probably met. He had a project where he was trying to detect exoplanet data, exoplanets in celestial data, right? Where you can kind of detect an exoplanet, or you can detect objects that are going around a star by frequency of light, right? There's going to be some dip in the frequency of light, and so you get this nice linear signal, that repeats. And there are times where we can verify that there's an exoplanet in some sort of repeating phenomenon that's observed in relation to a star, in terms of dips in light or jumps in light. And here's the problem with this data. Let's say you have 50,000 rows of data, and only 40 to 50 exoplanets detected across those rows. If you want to make a very accurate prediction of the presence of an exoplanet, you can just write a print statement that says no exoplanet detected, because you're going to get that right 50,000 minus 50 times out of 50,000. And that is, again, that's a bigger issue than the idea of an outlier. Outliers are informative, whereas missing data or imbalanced data, in that case, is really problematic. So what we tried to do is synthesize new data based on prior signals, where we look at the exoplanets and we're like, okay, can we make something that looks like this reasonably out of the signals that we have present? Can we generate new versions of this and make the data, instead of being extremely imbalanced, only somewhat imbalanced, in order to make a better predictive model? That's the kind of stuff that you find yourself doing in, that was for fun, but that's the kind of stuff you find yourself doing in the data science space. You're like, okay, well, we don't have this. Can we make this? Is this possible? And you find creative ways, and then you try to figure out if that creative way actually will be helpful. And in a lot of cases, like in that case, it kind of worked, but it didn't work it didn't work well enough to advance the kind of larger collective work on that project, on that exoplanet data. Like, it didn't do any better than other people's projects who didn't do that, if that makes sense. So yeah, the battle is not necessarily in detecting outliers, and outliers are more often than not just really helpful in terms of understanding the phenomena that you're observing. Oh, interesting. Every once in a while, Zoom tells me that it signed me out. I don't know if that happens with Clark as well, but I think, I'm not really sure why that happens. Okay, so we're gonna start thinking about variance, and variance we can think of as, in some ways, as being like IQR, but somewhat more sophisticated. And it's sort of like when we think about the mean versus the median. The median is kind of boneheaded, right? We just aim for the center of the data and we take that data point, and we kind of like just ignore everything else. That's what we do with IQR as well. So the relationship between mean and median is very similar to the relationship between variance and IQR, where variance has slightly more complexity. It's more related to every data point, as opposed to just a chunk of the data, a specific chunk of the data. So, making that parallel might be helpful in thinking about variance. Simply stated, the variance is the average squared distance between each data point and the mean. So what does that mean, right? Well, think about it. It's a distance metric, right? We are thinking about the mean, and then we're looking at each data point. And maybe I'll just make this a little bit more visual. Okay. I can draw lines on there, but I cannot erase them, which is cool. Okay. So if we're thinking about data, and just, simple numeric data where we have some line, right? And we can put bounds on this, let's say 0 to 50. We can have, let's say we've got a mean somewhere around 63. Every data point, let's say we've got another data point here, we can measure this, right? We can measure this distance. Let's say we have another data point here. And maybe this is, 7, and this is 15. The average distance here is going to be 11, right? If we only have these 3 data points at the mean and these other, what we know to be the mean, let's say, and each of these data points, then we can see that the average distance between these 2 data points and this value 63 is, 15 plus 7 divided by 2. Now, variance does this, we think because we can be above or below the mean, we make this slightly more complex, right? We say this is actually going to be the distance between each data point and the mean is going to be 7 minus 63 squared plus 63, sorry, plus 15 minus 63 squared. And if we had more data points, we would continue doing that, and we would divide this by the number of data points, right? So we'll call that big N. What does this tell us? Well, it tells us exactly what it sounds like, the average distance between each data point and the mean, except we're squaring it, okay? That's important to remember with variance. We have, if you think about what squaring these distances means, it kind of takes things out of scale, right? Like when we think about a room, when we think about the dimensions of a room, well, it's almost easier to describe a room as being 5 feet by 8 feet, right? That's meaningful in a way. Like we can conceptualize that. Oh yeah, it's 5 feet on one wall and 8 feet on another wall. Well, what's the square footage of that? That's 40, right? That's 40 square feet. Now, 40 square feet is harder for me to conceptualize. I actually, in my head, I break it into something multiplicative, I try to take the square root of it in my head. That's how I approach the idea of square feet. Variance, you're going to need to do the same thing because, well, let's just look at the formula for this. The formula for variance, there's actually 2 formulas, but we'll talk about that next time. The formula for variance, and this is the variance of a population. This is sigma. So sigma squared is going to be the sum of, well, we'll start at the first value and go and sum all the results of this. The sum of each data point in a data set X, right? So X could be, 5, 3, 9, 27, 14. How about that? Each data point and the mean of the data squared. Now, what we do after all that is we divide it by the number of data points, n. Okay? So if you think about what this is doing, and I'll just calculate this really quick. I'll bring up a Python terminal to do that. So 5, 3, 9, 27, 14. So, right, maybe I can, well, I'll just do this by hand, right? So this will be the sum. Oh, probably need to actually be using Python. So we'll do the sum of okay, so that's 5, 3, 9, 27, and 14. And we are dividing by, what is that? 5. So there's our mean, right? 11.6. So I can build, you know, a function that will take each of these values, right? So what is this? This is like 11.6 minus 5, right, squared, plus 11.6 minus 3 squared,
right? It the other way around?
It actually doesn't matter.
Okay.
Yeah, because we're squaring it. Squaring in this case is also going to get rid of the negatives. So it'll be equivalent either way. 11.6 minus 6, yeah. 11.6 minus 3 squared, and then 11.6. Right, this is kind of tedious, right? It's better to do this in a function. But we'll start off next class with writing that function, actually. 11.6 minus 27 squared, and 11.6 minus 14 squared. Okay. And then we're going to sum all of that is summed, and I'll just say summation is going to get the result of that. Hopefully there isn't an error in there. Doesn't look like it. So we've got our summation, and we can divide that summation by 5. So what does that number mean for us? 73.44. It's not great, whatever's happening there. It's something that is hard to interpret. And some people get very used to interpreting variance, just as people who put in flooring get really good at interpreting square footage. If you're not putting in flooring all the time, you're probably not able to conceptualize square footage effectively, or selling houses, or whatever it is that is specifically engaged with square footage or square area. But we can pull this back in to the realm of understanding, let's say, by simply taking the square root of it. So the variance is the squared, the sum of squared differences, the average sum of squared distances between each data point and the mean. And then we have another much more helpful metric that is simply the square root of that, okay? And that's our standard deviation. When we're talking about standard deviation is the square root of the variance. So that's as simple as raising this to the 1/2. And that kind of makes sense, right? 8.56, let's say 8.57 looks like, it's kind of the average distance between each data point and the mean, right? If our mean is, 11.7, I just, typed it 30 times, 11.6. If our mean, and I am going to refer to it here as mu, if that's 11.6, that seems pretty well representative, right? 8.57 seems like that's a good number to consider between each of these data points and 11.6 as being the average of those. So let's call it here. In next class, we'll wrap up variance and standard deviation, and what we'll do. We're going to deepen this concept just a little bit. There's something a little bit theoretical. Well, I don't want to say theoretical. There's something we do here when we are considering samples. Okay, what we've done here is thought of the population variance. So that's our population variance, which we represent as, sorry, not S squared, but sigma squared. And of course, to get the standard deviation, we just take the square root of that. And we refer to the standard deviation as sigma for a population. Okay, I'm going to go ahead and stop recording, and just give me one sec to do that.